All right. Welcome to my talk about an integrated video investigation tool for video forensics. And my name is Chengchao, and I'm from the Fraunhofer Institute in Germany. First is motivation for the development, because in recent years, public security has been a major concern among public, and video data is one of the most important means for doing criminal investigation. And nowadays we have a lot of video data. For example, we get data from public or private CCTVs, or we can get videos from the smartphones by the witness at the crime scene, and we also have mobile or wearable cameras used by the police. So the problem is how to process and analyze this mass data efficiently. For example, we have to do an analysis, re-identification, documentation, and the final report. So this is the typical workflow of normal forensic video investigation tasks, and we have as input a lot of image data. They are unstructured and partly also have without metadata, and they may also have different codecs of formats and qualities. So if we start a document or a file, and we have to replay and examine the data. So in order to do this, we have to turn to different tools, for example, FFmpeg or VLC, etc., to investigate a crime scene, and using some prior knowledge, for example, the description from the witnesses, and for example, what time and what the place is of the crime. And if we found a suspect, we have to document the video clips of the crime scene to reconstruct it. And if new evidence emerge, and we can repeat this loop. And finally, if we have finished reconstructing the crime scene, we should again use different tools to edit the video data, and to add some documents using some office tools. So at the end, we export the report, and either to hand over to police authorities or for archiving. And so, in summary, video investigation has some text. For example, we have to do visual investigation, and we based on video data. So we have to do very efficient management and processing, and we have to do search and recognition tasks, and we also need some facial composites for a suspect if we don't have any data in our database. So the problem is that nowadays the tools don't have still have a lot of manual steps, and for example, they don't have efficient steps to process for navigation in the video data, and for efficient analysis. And all the documentation and the report steps are mostly done by hand. And another important step problem is that we have a domain gap, because for surveillance cameras we usually have a wide-angle lens, and so even with some HD cameras we still have some very small field of the imaged face or the person. So we have to deal with it. So the challenges in this kind of task is that we have first to filter out a lot of irrelevant data. For example, we can do temporal filtering or spatial filtering, and if we don't have a photo of this suspect, we have to do extensive search in the mass video data, and for crime scene analysis, we have to play forward and backward in the video data to reconstruct the scene. And sometimes when the image data is not good enough, we have to apply some enhancement applications. And also important is that for the documentation, we have to log all the steps so that the evidence will be valid on the court. So first, I would introduce some the software components of the ivisX system, and this is the workflow of the system, and it looks very similar to the typical workflow. But there are some differences. For example, we have the digital repository of documents and videos, and we have developed some tools for visual analysis, and we also have integrated video editing tools for generating the reports, and finally all the reports are archived digitally in our system. And additionally, we have also introduced a novel 3D face super resolution framework, so that if we have very low resolution faces, we can generate a 3D face with high resolution texture. And the output can be fed into the search module or to the final report as the facial composite. Yes. So as summary, we have developed easy to use modular software architecture consisting of different standalone softwares, and they are integrated into a complete tool. So at the moment we have 6 modules: the replay module, the core module, the geomap, the search module, the face 3D, and the report module. As I said, they can work standalone independently. Also, they can communicate with each other with a lightweight inter-process communication protocol. And the first module is the ivis Core. This is the main application launcher of ivisX. And after it launches all the components, it shows a list of the synchronized videos. For example, we can see that here we have 3 videos from static cameras with very similar time span. And here on the left we have a mobile clip from some mobile phone, but with different timestamp. And then in the next module, this is the ivis replay. These videos are shown here. And for example, these 3 videos are synchronized, and this is not. So at this time point, this video is not shown. And ivis replay is the multi-stream player for doing crime scene analysis, and it has the job mainly to do temporal filtering. And when we interact with ivis replay, and the timestamp will be sent to other modules, for example, for search and for face resolution. And we can also define the time span that we need for the final ivis report. And then this is a geomap module, and we can see that this is the module shows the 2D view or 3D view of the scene, and we can see that it also shows the cameras, and it can also show detections and trajectories of the suspects. And so this module mainly has the function of spatial filtering. And but note that we need the geo referencing of the camera, so it's only the 3 static cameras here are shown. And the next module is the ivis search, and it works as a appearance-based content search algorithm. And it can receive input from other ivisX modules, and also maybe from the external sources, maybe from other authorities. And if we get a crop from maybe ivis replay, and we with one click we can have a ranking list of the similar appearances in all the videos. And upon click on one video, we can either jump to this video containing this frame, or we can send this video to the final report. And at moment we have only appearance-based texture model for face and for upper body, and in the next we are planning to add our other algorithms in our lab. For example, the face re-ID and person re-ID into the ivissearch module. And the next one is the new Face 3D module. And as an input, we can see that we have a low resolution crop, maybe from Ivis replay. And then with one click, we can have a high resolution the 2D image and a high resolution 3D face of this person. And we can, because we have everything in 3D, so we can maybe rotate this face to get a novel view, a frontal view of the input image. And the last module is the Ivis report. And after getting all the results from other modules, we can merge all the videos, images, and facial composites into the final module. We can see that also the videos and also the output of the Face 3D is also input into the final report. And we can do video editing and merging, and we then can add text to the frame. So we can, in the end, we can generate a single report consisting of different images and videos. So that's from the software side of the ivisX framework, and I will give some brief introduce into the algorithmic components. The first one is the 3D face super resolution. And for doing that, we have three major steps. The first one is the landmark detection, and the second one is to reconstruct a dense 3D model of it. And using the 3D dense model, we can recover the high resolution 3D texture using the training data. And here I will give some introduction into the final parts. And this algorithm was introduced also in the last year's WACV here. And for super resolution, we have offline a trained database of faces, and because we are doing 3D, we first extract a 3D texture of all the faces in the database. And now, given an input low resolution image, we just reconstruct the 3D shape and the 3D pose of the face, and then we just project all the trained data with respect to the 3D shape and 3D pose onto the input frame, so that with the registered data we can use face super resolution algorithm to get a high resolution output. And the problem is that we have here 3D data. For example, this is the formula of a normal image formation model, and we know that for super resolution we have the problem of inversing this problem. For example, we have a high resolution input of X, and we add some motion to it, and then combined with blurring and downsampling, we have a low resolution output of Z. But here we have a lot of scattered 3D vertices of the face, and how we can connect these vertices into the grid data of the Z. So we proposed a very straightforward 3D to 2D interpolation scheme. And first, we just subsample the data points, so that we have at maximum only one vertex within the grid of the pixel. So we can see that we have a lot of holes here, and then we do triangulation, so that for each grid point we have three surrounding vertices, and then we just form an interpolation matrix, so that this matrix has as many rows as the number of pixels and as many columns as the number of the vertices. So for each row, so that is for each pixel, we have three entries of the barycentric coordinates, and then to get a 2D image, we just multiply the interpolation matrix with the 3D texture. And we can also apply motion, and also we can integrate blurring and subsampling into this operator to get a low resolution output here. So for doing super resolution, we used a patch-based method because it's more robust to many challenging environments. And first, the pictures are divided into overlapping patches, and for each patch we decide which of the vertices belong to this patch, and then for each vertex, for example here we just use the train data to reconstruct the patch, and then after reconstructing all the patches we have immediately a high resolution 3D face. And this is the output of this input image. That is one of the suspects in the process bombing. And here's the 2D and 3D output. And the second mode is the person re-identification. And we have priorly experimented with handcraft features like the covariance features, and we also tried the CNN feature that has a similar network architecture as the Google Net, and it's trained using the standard classification task on this data. So we know that both handcrafted features and CNN features have their advantages and disadvantages. So we just come to the idea that if we can combine these two features, but the problem is how to combine those. So the first idea was to do an element-wise addition. So just it borrows ideas from the ResNet. So the CNN has only to learn the offset of the handcrafted feature, and then we can also concatenate the features and also add fully connect layers to learn how to combine. So in practice, in this paper, we know that the concatenation works out best. So these are two modules, and as a conclusion, we have proposed easy-to-use framework for video investigation for multiple displays, and for future work, we plan to add more modules in the ivisX, and we would like to add a georef module so that we can georeference the images and videos within the framework, and also we would like to add an indexer so that we can have efficient database search after importing data. So that's all. Thank you very much.
All right. I think for the sake of time, I'll just ask a question. Can you comment on, you mentioned that your super resolution was patch-based.
Yes.
Comment on, I guess, some of the artifacts of that, because generally when you do patch-based versus a holistic approach, you generally get it boundary effects.
Yes. I use one pixel overlap of the boundary, so at boundary region it just used the mean of the vertices value, texture value. So in practice we don't observe many maybe we don't observe any artifacts.
Okay. And I guess a follow-up question is, because there's a lot of components in your framework, I guess, what do you see as given that this is a cross-domain biometrics, what do you see as the major cross-domain component of your framework?
I think it's this the cross resolution domain. So we can improve the resolution and use to improve the image for the search and also for the manual search maybe as the facial composites.
All right, let's thank our speaker.
Thank you.